Starting with the name of Almighty Allah, I am Saqib Mahmood. I am here to present my final year projects, which we have done under the supervision of Engineer Dr. Qasim Ali and with my group mate Shehzad Gul. So the title of our project is Simulation and Hardware Design of 3 kilowatt brushless DC motor for light electric vehicle application. So I will start my presentation with the thank you note for our worthy professor, Dr. Qasim Ali, for his continuous encouragement, feedback, and support that is invaluable for us throughout this process. So this is the content of today's presentation. We will introduce what is BLDC motor, our aim and objective, literature review about the software on which we have simulated our models so that we can proceed for the hardware design. NSYS Maxwell RM Expert Library results, 2D and 3D results, animation of the motor, and then conclusion and references. So, starting with the introduction of the BLDC motor, that BLDC motor is the permanent magnet synchronous motor which is electronically commutated. It has a permanent magnet on its rotor, and the rotating magnetic field is produced in the stator, which is winded. So electronic commutation removes the brushes and commutator arrangement from the BLDC motor, making the motor more reliable and noise free. Also, it is used in variety of application from the consumer electronics to industrial machinery, electric vehicle, robotics, and so on. So, what is the problem statement is that the Earth every temperature is increasing every decade. According to the UN report, they states that the Earth every temperature is increasing 0.2% every decade. It is because of the because of the reason that mainly our transportation is on the internal combustion engine which use fossil fuels to run. So they release toxic gases including methane, carbon dioxide, and nitrogen oxides to the atmosphere, which aids to the global warming. So we know that the fossil fuels are limited in quantity in Earth, and as we know that internal combustion engine run on fossil fuel. So with the time and as our need increases, the fossil fuel reserves are depleting, and the EV industry is booming nowadays. And in light electric vehicle, they use a BLDC motor to as a drive unit in it. So what are the aims and objective of our FYP is that we want to make we want to make a motor that is more efficient and directly use renewable energy, because we know that renewable energy from all the sources from which we can get the renewable energy is in form of DC. So without the conversion losses, we want to directly use it. Lower emission, there is only heat emission in the heat dissipation in the electric motors. So no toxic gases like methane, nitrogen oxides, and carbon dioxides. If we use BLDC as a drive unit in the light electric vehicle, as discussed earlier, that it does not have any brushes and commutators, so the maintenance is reduced, and if you use EVs instead of the vehicles that use internal combustion engines, so we can save our cost in terms of transportation cost or running cost. That is estimated that if we move if we use electric vehicle and electric vehicle for our transportation, it use 1 to 2 pkr per kilometer uh, to move from one place to another, while that of internal combustion engine use 9 to 10 pkr per kilometer. So from the literature review, as we started our project, we went through many papers regarding brushless DC motor. Each and every paper states that it's more reliable, and obviously it is nicely separation of the BLDC motor. It requires low maintenance. Um, what's the interesting fact about the BLDC motor that it has high power density. Comparing it with other electric motors, it has small size but gave the same output is other motor having larger size, and it has efficiency greater than or equal to 85%, and the motor can be precisely controlled. Its torque and speed can be controlled precisely. So about the software, INSYS Maxwell software is there are many software for the electric machine design in the industry, but we as our supervisor uh, recommended us to use this INSYS Maxwell software. Another reason is that it is very friendly to use. And the third reason is that other design the design from the other software can be imported and simulated for the output parameters which we are which which are under consideration. So INSYS Maxwell software are used for the simulation of electrical machines and many other applications. It uses finite element method for calculating the electromagnetic parameter of electrical machine. What it does that the model we have selected in the INSYS Maxwell software, it divided to many small interconnected portion in which we call mesh in the software terminologies. So for each finite sub region, it solves different equation which include Gauss's law, Ampere law, Gauss's law, electromagnetism, and then it calculate and make approximation about the magnetic field, flux values, voltages, currents, and other parameters within the machine. So this figure shows the mass division by INSYS Maxwell, so, which is a small interconnected portion of the motor, and these are the equation which it used for the estimation of the electromagnetic properties of the motor. So starting our FYP and simulating the models on the INSYS Maxwell software, we simulated mini models of 3 kilowatt BLDC motor, of which we have selected these three models to compare and present here, and then select one for the hardware design. So 36 lot 12 pole motor of which parameters are bolded here. So we selected this for the hardware design. From this table, we can see that the staking factor are kept same for each motor. Staking factor is the ratio of the actual length of the stator divided by the length of the steel, only steel. So inner diameter of the stator is kept constant for the two model, but for the third model it is 140 millimeter. Taking into the consideration the design parameter, the designing parameter of the motor, we kept the axial length as low as possible, is 30, 40, and 45 millimeter for each model. Moving toward the stator dimension, in stator dimension, we kept the air gap is constant for all the three model, membranes and type of steel for all the three model. Length of the rotor and the stator is same is we want that both the part of the motor stator and rotor are concentric and of equal length. So uh, maximal radial length of the motor of the three of among all the three models is 300 millimeter, and the minimum length radial length of all the three model is 270 millimeter. Thickness of magnet do play important role in the magnet motor output parameter, so we read it as well. So When we when we entered the stator diameters of the different model into the motor, so it generated us four different slot types, of which we selected this slot type, which is regarded, which is no denoted as slot type one in the NSYS Maxwell software. Uh, for all the three model, we selected the same model, but due to the different length of the stator of all the three model, these parameter of the motor varies, which we can see in the coming three slides. So the slot design is same, but these parameter varies because the radial length of the rotor varies for each model. So this is the slot type for 36 and 12 pole motor. So next is the cross-sectional view of BLDC motor. So for 24 slot 8 pole motors, we rated the motor for 3000 watt or 3 kilowatt. We want to run this motor with 48 volt voltages DC. Rated speed we kept 800 RPM. So by converting it to kilometer per hour, it is approximately 65 kilometer per hour. So we want if we make the hardware of this model, we want the maximum achievable speed of the vehicle is 65 kilometer per hour, and this is the number of the poles in this motor. We selected it is 8 poles per for this model. So for 51 slots and 40 pole model, we selected 40 poles, but we wanted to run this motor on the 60 volt DC. Also, the speed and the rated power was kept constant for this model. For 36 slots 12 pole motor, we kept the rated voltages as 60 volt, rated power 3000 watt. Number of poles was changed because this is the whole new model. So we kept the number of poles as 12 and the rated speed. So in this model, we want to achieve that if the motor is of 3000 watts, so we must achieve maximum speed with it. So we kept the rated speed as 1500 RPM, which by converting into kilometer per hour gave us up to 105 kilometer per hour, which is a very good speed. But for this model, we have to compromise on the torque. So after that, the motor gave the software, NSYS Maxwell software gave us the stator winding configuration for all the model. For 3 kilowatt model, 24 slot 8 pole model, it gave us two layer concentrated winding arrangement. For what is the concentrated winding is that the slot per pole per phase ratio must be less than 1. So for that, it gave us the concentrated winding arrangement. Same is for 51 slot and 40 poles motor, which also gave us a two-layer concentrated winding arrangement. But for the for the 36 slot 12 pole motor, it gave us distributed winding arrangement in which that slots per pole per phase ratio was equal to 1. And for the hardware design, we done both distributed and concentrated winding arrangement. So to check the output parameter of the motor. So these were the winding stator winding configuration given by the NSYS Maxwell software. And now coming toward the results of RM Expert Library. So for the first 24 slot 8 pole motor, we kept the rated speed is 800 8,800 RPMs. So for the 800 RPM at the rated speed, it gave us 52 Newton meter torque, and at the speed of 1048 RPMs, it gave us a torque of 13.55 Newton meter. This results were taken for the constant load. For the constant load, so we for each point, if we multiplied the torque and the speed, we will get the output power of 3000 watt. So this is the efficiency versus speed graph. So for the rated speed, the motor efficiency was 73% which was not good, because from the literature we have studied that it gave us efficiency of that the BLDC efficiency is more than 85% or equal to 85%. So at the rated speed, it was not that efficient. So that model was rejected, and the maximum efficiency achieved was at 1046 RPM, which was 83%. So coaching torque of the motor was high. So what is the coaching torque? Coaching torque is the interaction between the stator teeth and the permanent magnet. As the rotor is made of permanent magnet and the stator teeth is made of steel, which was M15 29G type steel. So there is interaction between this permanent magnet of the rotor and teeth of the stator. So this torque opposes the produced torque in the motor and eventually affect the net torque of the motor. So 0.94 or 1 Newton meter of the coaching torque was produced in this model. So we tried to minimize it in the other model. Let's see what is the result in the other model. So this is the torque of speed versus graph of speed versus torque for 51 slot 40 poles motor, and from there from this graph we can see that at 785 rpms are near to the rated speed of 800 rpms, it gave us 36 Newton meter torque, which is a very good value. And this motor is efficient at the rated speed, and it confirms the literature review that we have studied, that it has 85% or greater than efficiency. So at the rated speed it is 85% efficient, and the coaching torque of this motor is 0.79 Newton meter. As it gave is from this graph we can see that it has a 36 or up to 37 Newton meter torque, and this coaching torque of 0.79 cannot affect the net torque as much as of the previous model. So this model is good because it gave us high efficiency of greater than 85% for the rated speed, and gave us 36 Newton meter torque. So this is the torque versus speed graph for 36 slot 12 pole motor. And as we kept the rated speed at 1500 rpm, so it gave us 28.38 Newton meter torque at 1302 rpm. So both the values of speed and torque is good. So this model can be considered for the hardware design, and we did so, which we will discuss further in this PPT. And at 1302 rpms it gave us 86% efficiency. So this model was efficient of all the model, and we go forward for the hardware design of this model. Also, the coaching torque is minimum of all the three models, which is 0.27, and it cannot affect the net torque of the motor, which was 28 Newton meter. So if we subtract 0.27 Newton meter of the 28 Newton meter, it cannot affect the net torque, and it is also the lowest value of all the possible coaching torque values. So moving toward results of Maxwell 2D design, as we enter the design parameter into the RM expert library, it gave us the estimated value of the output parameter of the motor. After then we can move to the 2D design of the motor by just one click, and it gave us the best possible output parameter of the motor by calculating it and making the mesh and dividing the model into small finite portions called mesh. So let's see the full view of motor in Maxwell 2D and 3D. So for this is the 2D model of 3 kilowatt motor of 24 slots and 8 poles, and this is its 3D view. So by simulating this model in Maxwell 2D, it gave us that it draws 85 ampere of RMS current, which is a pretty high value. And from this graph we can see that And from this graph, we can see that the waveform of the current is trapezoidal. And from the literature review, we have also studied, we have also came to know that the back EMF and the current drawn by the BLDC motor is actually in form of BLDC motor. So the simulation confirms that. So this is the graph of the moving torque in Maxwell 2D from in which we can see that the maximum value of the torque that can be achieved for the 24 slot 8 pole model is 39 or 40 Newton meter. Average value is 30 Newton meter and the minimum value is 29 Newton meter. The torque ripple is here 34%, which is pretty high. So we tried to minimize it in the other models. This is the magnetic saturation and flux line distribution. So the magnetic saturation of this model goes high up to 2.48 Newton Teslas. So due to which there is very much heat dissipation in the winding of the motor, is a high rotating magnetic field is produced. So we need to have proper heat dissipation mechanism for this model. And from the flux line distribution, we can see that the flux is uniformly distributed and is moving through the stator and the rotor steel part. This is the animation of the 3 kilowatt BLDC motor for 24 slot 8 poles motor. We can see that the motor is running in the simulation and the time is changing, speed is constant, 876 RPMs, and position is varying. So moving toward the full view of motor and Maxwell 2D and 3D of 3 kilowatt 51 slot 40 pole motor. So this is the 2D model of the 3 kilowatt 51 slot 40 pole motor, and this is the 3D view. From 3D view, we can see the axial length, and from 2D view, we can actually take the approximation of the radial length. This model radial length was the this model radial length has greatest radius of all the three model. So this is the moving torque graph of 51 slot 40 pole motor, in which we can see that 50 Newton meter is the maximum value and 31 Newton meter is the minimum value. Average value of this this model we can take is 38 Newton meter is the average torque, is the average moving torque. From this graph, we can calculate the torque ripple is the torque maximum minus minimum divided by average multiplied by 100. So the torque ripple was 50%, which is a pretty high value, and we try to minimize it in the next model. So this is the current. Actually, this model was drawing 50 ampere of current, which is way less than the 80 amperes which was drawing the other model of 24 slot and 8 pole motor. So this was the advantage of the of current rating. So the magnetic saturation in this model was up to 1.89 Tesla, which is pretty low and below the standards of 2 Tesla. And we can see that the flux lines are distributed uniformly and is moving through the stator and the rotor steel. This is also the animation of 3 kilowatt 51 slot 40 poles motor. Let's play it. So it was recorded for the less steps, so it is moving slowly. But we can see that the motor is running properly in the simulation. So this is the 3D and 2D and 3D view of the 36 slot 12 pole motor. We kept that the axial length of this motor is 30 millimeter. We can see that the stator is kept inside of the motor, inside of this model, and the rotor is outside, and this is the 2D model. So this is the moving torque of the 36 slot 12 pole motor, in which the maximum value is 34 Newton meter and minimum is 25 Newton meter. And this transition occur every 0.38 millisecond after the steady state. So the average value is 29 Newton meter for this. If when we calculated the torque ripple, it was 29%, which was minimum of all the models. And considering this value with many other value, we go for the we went for the hardware design. So this model draws current of 70 amperes per phase, and from the graph we can see that all the three phases current is properly trapezoidal. So the magnetic saturation of this model was up to 2.21 Tesla, which is lower than 24 slot 8 pole motor, but slightly higher than 51 slot 40 poles motor. But uh, for, but if there is high value of magnetic saturation then 2 Tesla, then there must be the proper setup for the heat dissipation of the rotating magnetic field that is produced in the stator, and we did consider that particular parameter in the hardware design. And flux distribution, this is from this graph we can see that the flux is uniformly distributed, is moving to the stator and the rotor steel. And the maximum value of the flux line distribution is 0.0184 Weber per meter, which is highest of all the three models. Uh, so this is the animation of the 3 kilowatt 36 slot 12 pole motor. So from this animation we can see that the motor is uniformly moving with constant speed with the magnetic saturation of 2.23 maximum, 2.23 Tesla maximum. So then RM expert RM expert library can calculate as the material consumption of the motor. So for the 12 pole 36 slot motor, there is the minimum consumption of the permanent magnet and the minimum consumption of the armature core steel. Also, there is the minimum consumption for rotor core steel, and the total net weight of the 36 slots 12 pole motor is 9.96 kg. So that's why we went for this design. Also, for the electrical and mechanical output of the motor, we from this table we can see that the 12 pole 36 slot motor is efficient, is maximum efficient, is has efficiency of 87%, and it is maximum speed of all the three models. Losses are very less in this model. The torque ripple is 27%, and the highest magnetic flux value can be achieved in this model. So after the comparison of all the three model, we went for the hardware design of 12 pole 36 slot motor. So this is the hardware of the designed BLDC motor. This is the stator which has 36 slots, and this is the rotor with the permanent magnet which is stick to the rotor steel with the epoxy, and it has 12 poles. So this is the permanent magnet used for the hardware design of 36 slot 12 pole motor, which has a thickness of 6 millimeter. So this was the shaft setup. This is the bearing. This is the steel, and this is the shaft for the for setting up shaft in the stator, as we were designing the outrunner motor. So by assembling the shaft setup in the stator and then winding the stator and connecting all the three phases to it, this is the assembled motor, which of 3 kilowatt motor 36 slot 12 pole. So this is the top view, and the other one is the side view of the motor. And this is the working model. We actually captured the video of our working model, in which we have discussed everything. Let's see. So coming toward the conclusion for 3 kilowatt motor, 36 lot 12 pole motor, that it is higher, it have highest efficiency of all the three model, and it has good torque with respect to speed. We see that torque of 29 Newton meter with the speed of 1302 RPM or 105 kilometer per hour if fitted in the hub of a motorcycle. So this is a very high speed that we can achieve with this motor. So from the table shown before, we came across that it has minimum material consumption and the net weight was minimum of all the model, that was 9.8 or something kg per kg. So if the material consumption is minimum, it implies that this motor is the economical of all the possible model. If we have to make the model of all the hardware model of all the three simulated models, so this one will be the most economical of all the one of all. So as discussed, it was having 0.0184 Weber per meter for flux, magnetic flux, so which was highest of all the values. So overall, it was having a low torque ripple of 27 or 29%, comparing to the 34 and 50% of the other two models. So it was having low torque ripple of all. And what is uh, what is most different of this model is that we manufacture it locally with minimum resources available. And 105 kilometer per hour speed can be achieved if we fit in the motor, a motorcycle tire having diameter of 17 inches. So what is the future work or recommendation of, so we have tested this model as I show the video that we tested it for the no load operation. So in future it can be tested for the the hardware can be tested. As the hardware is manufactured, it can be tested for the full load operation, its voltage, torque, speed, current can be calculated in the future, and with some mechanical changes. It was not ready for to be fitted in the hub of electric bike or motorcycle. So with a minor mechanical changes, it can be used to use it in the hub of electric vehicle or electric motorcycle. So these are the future recommendation. So these are the some references that we used while accomplishing and modeling of our hardware design. So thank you for listening us and subscribe the Sakkari University Electrical Engineering Department YouTube channel, Electrical Engineering Subayu on YouTube, and do like it on Facebook as well. Thank you.